So welcome to the GCSE Physics live stream part of the session this evening. This is going to be between 7:30 and 8 o'clock roughly, and then from 8 o'clock until 8:30 roughly I'm going to be doing some A-level physics. Now if you're doing GCSE Physics, then I hope everything is going well. You still have plenty of time before your exams. You've got maybe 1 month until paper 1, a bit more than 1 month, and then maybe almost a couple of months until paper 2, so loads of time. Now, the revision tonight, it's going to be for anybody doing any exam board. So it doesn't matter if you're AQA, OCR, EdXL, and that's the same for GCSE and A-level. I'm trying to keep the stuff at the moment because I know there's so many people watching, and it'd be great to let me know in the chat at the moment which exam board you're actually taking, because it's always good to know the sort of mix of people I have on here. But the actual questions I'm doing for GCSE, these are from some practice papers that I've made, and I based these on the AQA specification. However, the actual content is going to be suitable for anybody. So ideally, this is for AQA higher triple, which I know a lot of people out there are doing. But also, if you're doing EdXL GCSE, like free maths lessons is, then this is going to be absolutely fine. Somebody says, AQA, you're pretty sure. If you're not sure which exam board you're doing a month before your exams, just maybe go and check. Have a look on your exam timetable, see what it says. However, everybody does paper 1 on the same day for physics. Everybody does paper 2 on the same day. It doesn't matter which exam board you're doing. But these questions are AQA ones. And what I have here is just an example. Again, this is just my kind of my ruse really to get all of you to buy stuff in my shop. But basically what I have are a series of extra practice papers. I've got 12 in total. This paper here, you can see it's got all of the questions as you'd normally have in an exam. So you get that as part of like a digital download. Also, you get the mark scheme, which is a bit easier to read than the ones you get in real past papers. But of course, I do other things. I also have work solutions. So as part of the digital download, you also get work solutions for every single question. And that means there's 12 papers of 10 questions each, so there's 120 questions, all with work solutions. And also, if you have a premium plan or your school subscribed to my website to see everything, then if you go to this link over here, so this one is practice-AQA-physics-1-theta. If you type that in, then you will find full worked video solutions to all of the questions as well. So there's a lot of stuff out there, and this would be ideal for looking in the comments. People like Angus, Wilf, Ollie, Physics, so many people out there, this would be ideal for you. But today, we're going to be going through some questions initially to do with waves, okay? It's only really if you're doing triple science that you need to know a bit more detail about sound. But here we have a question. I'm going to approach this in the similar way to how I've approached questions in previous days. So this is just a technique that if you get into the habit of just like underlining things, highlighting things, it's going to make everything else a lot easier for you. So this one here, this GCSE question, we've got a student connecting their phone to a Bluetooth speaker to play some music. Bluetooth basically uses radio waves, and they've got this frequency. We've got this given in gigahertz, and a giga is 10 to the 9. So something you do need to be aware of is that in physics we have these kind of prefixes in front of certain numbers. So you might be familiar with kilo, mega, giga, and tera. Okay, so these are all big. And then you go smaller, so we might have centi, we then have milli, and actually after that we have micro. Now we tend not to use micro at GCSE, but this is anything times 10 to the minus 6. A milli is 10 to the minus 3, kilo 10 to the 3, mega 10 to the 6, giga 10 to the 9, and a tera is 10 to the 12. But I think for GCSE, the ones you really need to be aware of are these ones over here. And it's always worth, if you see these in a question, maybe just underline it to show that there's a unit in some kind of prefix. Okay, and I can see that some people are already moving ahead, which is awesome. So we've got information about the speed. So I'm just going to highlight this. We've got a frequency of this number. Okay, so I'm just going to write the symbols down for this as well. So frequency is an F, speed is V. Okay, so that's just some data in the question. State whether the waves carrying the Bluetooth signals are transverse or longitudinal. Okay, so really the first thing we're thinking about is, and this is kind of the tricky thing, which I think a lot of people are in the chat kind of talking about. Is it longitudinal, is it transverse? Right. What we've got is basically a signal that somehow goes through the air and it goes from the phone to the speaker. So this is basically our first wave here. Okay, and this one is Bluetooth. Okay, named after I think a Norwegian or a Nordic king or a ruler who was called Bluetooth. But of course then the speaker then emits sound waves. Okay, now the first thing is the waves carrying the Bluetooth signal, because these are radio waves, they must be electromagnetic waves, and all electromagnetic waves are transverse waves because we have these electrical and magnetic waves. And so the first one is transverse. Okay, so basically this is testing your knowledge, and I know why a lot of people might have said longitudinal, but the question is about the sound, the waves carrying the Bluetooth signal. So these are transverse. That's because they're electromagnetic. One of my favourite diagrams is this one here, which is like a 3D graph. And basically along this axis, we can maybe draw the electrical component of that wave, which is going up and down. And then side to side, we can draw the magnetic variation and how that changes with time. So that's the magnetic wave over here. I'm going to call that B. And basically this is going through air. So we have this transverse wave where the oscillations in electric and magnetic fields are at 90 degrees to the direction of motion. Okay, calculate the time period of the waves. So for this one, again, in the chat, let's get some, let's get you thinking, what equation are we going to use to calculate the frequency of, what calculation are we going to use to calculate the time period of the waves? Okay. T is 1 over f. Yeah, so T is equal to 1 over f. Now what we do here, as physics has already said, is we use a capital T to be the time period. So that's the time for one oscillation. Okay, so we always use a capital T to represent that. And that's going to be equal to 1 over the frequency. But the frequency is this massive number up over here. So that's 2.4 times 10 to the 9. Okay, now when you're doing this, as Will said, 1 over 240,000,000. So when we do that, it's 1 divided by 2.4 times 10 to the 9. And this gives a number of 4.1667 times 10 to the minus 10. Okay, now this is what we'd expect. And again, people have got the right answer in the chat, which is brilliant. So I'm going to give this answer because we've been given the raw data to two significant figures to really keep this consistent. I'm going to give my final answer to two significant figures. So that's 4.2 times 10 to the minus 10. And you'll notice there that what we're doing is we're dividing 1 by a big number, and that means we end up with a small number. So when we have these electromagnetic waves, they have a really high frequency, and that means there's so many waves per second, the time for an individual wave is going to be very, very short. Okay, calculate the wavelength of the waves, including the unit. Okay, so the equation for this is V equals F lambda. Now, of course, I remember that just because I'm a physics god, but for you mere mortals down there, what you need to do is make sure that you do learn this, but also check it in your data sheet. So the wave speed is equal to the frequency times the wavelength. So here the frequency, again, is what we found up here. So that's 2.4 times 10 to the 9. And we're going to multiply that. Oh, sorry, calculate the wavelength. Okay, maybe I'm not a god. Okay, the wavelength then is equal to the wave speed divided by the frequency. Okay, right. So the wave speed, it says up here, is 3.0 times 10 to the 8. But of course, all of you knew that. All of you knew that because any time you have an electromagnetic wave, like a radio wave, it's going to be travelling at the speed of light, which is 3.0 times 10 to the 8 meters per second in a vacuum or in air. Okay, so 3 times 10 to the 8 divided by 2.4 times 10 to the 9. Okay, now for that one over there, I can see a lot of people have got the right answer. So we've got 3 times 10 to the 8 divided by 2.4 times 10 to the 9, which equals 0.125. Okay, so we can leave it like that. Right, someone's asking a good question about P and S waves. I'll come on to that. Vegetaval, I will come on to that just after I've done this bit here. So that answer is fine. So at GCSE, putting down a length of 0.125, and because it's a length, it must always be given in metres. That's fine for GCSE. You could also write it as 0.13 if you wanted to be really kind of pedantic, because that's given to two significant figures, like the raw data that we have over here. But at GCSE, they're not too fussy normally for things like this. So either of those would get you the mark. Yeah. Someone's asking about P waves and S waves in the ground. Now, what I do have is, for any questions which I don't kind of go through tonight, I do have videos about the entire GCSE course. And if you go to GCSE Physics Online, there's a link at the very bottom in the footer that has like the full video index. And I've got a full video there where I actually talk about these primary and secondary waves. And also I think I've got a question later on in one of my practice papers where I actually have a question about that and how we have the transverse waves that don't go through the molten liquid core, but the longitudinal other waves do. Okay, right. Do I teach maths as well? No, just physics, although physics is basically maths. Okay, we then have a kind of question that is typical in an exam. Okay, so the question here is kind of like a scenario. It's about maybe students competing against each other. The student says that you should use Wi-Fi to play music because the signal travels faster, and Wi-Fi uses the microwave part of the electromagnetic spectrum. State and explain whether their friend is correct or incorrect. So for this one, again, it's the first thing we're going to do is state. Are they correct? Well, what do you reckon? Yes or no in the chat. Rensburg family, you really like those lives. That's awesome. It's great to hear that this is useful. And really what we've got here is just like an approach to similar questions. Now, of course, I can't predict what's going to come up in your exams, but I can give you the tools and the techniques to actually approach similar things. No, says Katsroy. Is that how I say your name? Are they correct? Is their friend correct or incorrect? I would say we've got a no, we've got a correct. Does Wi-Fi travel faster than radio? Yes. Are they correct? No, their friend is incorrect. Okay. Yes, yes, yes. Right. So this is about they should use Wi-Fi to play music, not Bluetooth. So are they correct or not? Basically, Wi-Fi uses microwaves for the Wi-Fi, and Bluetooth, radio, both use EM waves that travel at the same speed. Okay, there we go. So Wilf said incorrect because all the waves on the electromagnetic spectrum travel at the same speed. Yeah, so the signal is going to go from that phone, which is kind of what the question is about. The signal from the phone to the speaker is going to travel at the same speed as it goes from this to this, and therefore they have similar properties. And you've got to be aware that electromagnetic waves have similar properties, so maybe they travel at the same speed in a vacuum or whatever, but they also have differences. It might be how much they spread out, about how far maybe how far they travel. So certain sorts of radio waves travel a different distance to other sorts of radio waves. So this question here was really about the similarity or differences between parts of the EM spectrum. Okay, yeah, so like Nathan said, it's not fast, but it has a longer range. Yeah, so physics says, as you go at the EM spectrum, it's only the frequency that increases and not the speed. So yeah, basically, if you look at the whole spectrum, so we've got radio, micro, infrared, visible, ultraviolet, X-rays and gamma rays, okay, all of these have the same speed. The difference is that this one here, the radio, has like a long wavelength and therefore a low frequency. The gamma will travel at the same speed, but it has a much shorter wavelength and a higher frequency, okay? Right, and because of that and the amount of energy they carry, we tend to have more energetic waves over here. These ones are ionizing, so gamma is ionizing radiation, X-rays can be ionizing, ultraviolet is ionizing, visible isn't. But yeah, they've got some similar things like that. Okay, now the next one I think is very much to be honest, this is probably more of a topic 2 question creeping into this. How does the speaker produce sound waves? Now for a question like this, there's 4 marks available. What I'm going to do though is I'm just going to start with a diagram. Okay, and this helps me kind of visualize what's going on. So in a speaker, what we have is a large cone of material, a bit like that. That's supposed to be my cone. This is attached to, underneath, this is basically going to be attached to a permanent magnet underneath. Okay, so basically this bit here is the cone. Here we have a magnet. And around the magnet, what we have is one coil of wire with a number of turns. So there we go. So what we have here is a coil of wire. Sometimes that coil of wire that carries an electric current is what we call a solenoid. Okay, and what we have basically is when you've got the coil of wire with a current in it, that's going to cause this to act as an electromagnet, and that's going to either repel or attract this magnet attached to the cone, and that means this whole cone is going to be going up and down and it's going to vibrate, and the frequency at which it vibrates is the same as the frequency at which this changes direction. Okay, and so what we've got to think about is for something like this, how can we get our 4 marks? Okay, think about writing in bullet points, think about this logical sequence. So what you might say is that a current in the solenoid makes, or probably creates, a magnetic field. This repels, sorry, it's a little bit difficult to write a full sentence, or attracts the magnet which is attached, so I'm trying to do this in colour, to the cone, so it moves with the same frequency as the input electrical AC signal. Okay, I think that's everything I need there for 4 marks. Okay, what I can see is that people, by writing in the comments here, it's really good, because this kind of, it's one thing to know it and be able to maybe describe it to your friend as you're having a chat, but the actual act of writing this down is the kind of thing that you need to practice. Okay, Nathan Hugh, can you write bullet points for 4 and 6 markers? Yes, you can. Okay, actually I didn't do it here, I probably should have written a bullet point, but basically bullet points are absolutely fine provided they're set out in a logical manner and provided you've got the correct scientific terminology and the correct physics in it. how does the speaker output two frequencies simultaneously? That is an excellent question. Some speakers actually have two cones. They've got like a woofer and a subwoofer, and so you might have two cones of different sizes for like the high and lower pitch notes. The other thing that you do is that basically you have maybe a signal like this with maybe like a low frequency sound wave. You add it to maybe a higher frequency sound wave, and then what we do with waves is actually called superposition, where we basically add the amplitudes of them together, and what you then get is a wave that might look like this. Okay, so basically we have maybe a low and a high pitch sound with different amplitudes, and what we actually get is something like this, which is actually what that speaker does. Okay, you don't always have to write in full sentences. I think you just got to be careful to write in short, succinct sentences. Okay, so that was the last part of that question. Right, the next one. This shouldn't take too long, so I've only got 10 minutes because I've kind of just gone on and on and on. Right, define a vector quantity. So again, in the chat, it's always useful to write this down. I would say define a vector quantity, and also, if you're doing it in the chat, do it in as few words as possible. OR4CL3, yo, hello. Free maths lessons, magnitude and direction. Yeah, so we could say a quantity with magnitude and direction. There we go, simple. Quantity that has both magnitude and direction, Excellent stuff from Randa, both the Nathans, Jules, great stuff. Yeah. Percy, great stuff. Yeah, Zeno, yeah, excellent stuff. So this one here, easy marks. Now, you know, when you do a question like that, it gives you a bit of a bonus because you know you've got those easy marks, you know it's correct. Right then, examples of vector quantities. What can we put down? So these are things which we often represent with arrows. So 3 examples. What I would say is we might just say force. I wouldn't say like, maybe we could have different sorts of forces. Acceleration, velocity. So we could have velocity, we could have acceleration, we could have displacement. Randa, great stuff. So we've got displacement. What else do we have? There's a massive list. Tension, yeah, that's a good one. So we might have tension in a string or in a spring, for example. Somebody said weight, which is good. The weight of an object is the force which is going to be acting in a certain direction. Anissa says momentum. Sorry, that's a P for momentum there. Not speed, normal reaction force. Yeah, normal reaction force is a good one. So lots of different sorts of forces. There's loads that you could have, and all you need to do is just be aware of them so you can put them down. Magnetic field, yeah, that's a nice one. Yeah, because the magnetic field, the magnetic field has a direction as well as a size. Is this useful for IB revision? Summed on the channel, not yet. That's going to be in 7 minutes' time as I go on to the A-level live stream, which starts at 8. Magnetic flux density, yeah. Magnetic flux density is basically a posher word for magnetic field. The next question, we've basically got a crane. So we've got a couple of cables. There's a load here, and this is being supported by a crane. Okay, so that's basically the scenario that we have. The first question is to, hopefully all of you can see that, state the force acting on the crane's load that is a non-contact force. So the way I'd be approaching this would be to think, okay, here's the thing, I'm just going to label the forces. So there's a force down. What is the name of the force which is acting down in this case? Okay, we've got some people already getting the answers in. Okay, so the downwards force, loads of people have got this right. This is weight. I've already said it, I think, for the last couple of days. I'm not going to put gravity. I'm going to put this as the weight. And there's going to be a force upwards. So what's going to be the force which is equal in size, but it's acting up? So what's the force there? So what is the upwards force acting on this load? And at the moment, we can say that this is in equilibrium. Tension, reaction force, thrust. This is where people are starting to maybe be a bit unsure. Obviously, if you're not sure, up thrust, no. Okay, so force here, I'm going to say is tension because it's provided by the cables. It's a bit like if you had a spring and you pulled a spring, it would be under tension. We've got tension in the cables. It's not upthrust because we only have upthrust in fluids like water. It's not a normal contact force because this isn't on the desk. If this was maybe, on the ground, if the load was on the ground, you'd have a normal contact force acting upwards. But at the moment, it's the tension in the cables. Okay, I can see some people retracting things. So looking at this, the non-contact force is the force where there's not things in contact, and that's the weight. And the contact force is the tension in those cables. Okay. Right, somebody says, pay me £5 for guaranteed grade 9. You don't need to do that. You just need to be in these live streams. And I reckon I could, if you do all these live streams, you buy my papers, I reckon that, you should definitely get a higher grade than you would do otherwise. Okay, Syrupy Gaming, yes, you are too late for GCSE, but you can obviously go to gcsephysicsonline.com/live, where you can re-watch all of this at your pleasure. Okay, we've got the mass of the load, calculate its weight. So for this, we know the mass, we want to know the weight, and we know that the weight is equal to the mass of that object times the gravitational field strength, which in this case is going to be 8,000 kilograms times the gravitational field strength, which I'm going to say is 9.8. But again, they will give you that number in the thing, and this then is equal to 78,400. Now you could give it as that at GCSE. I suppose because we only know that to two significant figures, we could maybe just give this as 78,000 newtons. Okay, the load is in equilibrium. Calculate the tension in one of the cables. So if we know that that force is in equilibrium, it means the force down due to the weight is equal to the tension force up. But of course, the tension force up is going to be provided by the tension in this cable added to the tension in that cable. So basically we've got the tension in one cable added to the tension in the other cable, and that size of the total upwards arrow is equal to the total downwards arrow. Now we know down, this is equal to 78,400. So we know the total force upwards is going to be equal to 78,400. But of course that's provided by the tension in two cables. So what we need to do is just divide that 78,400 by 2. So we're going to have basically the weight divided by 2, which is equal to 39,200 or 39,000 newtons. Okay, so basically we've got about 39,000 newtons in one cable, 39,000 newtons in the other cable, and that's then equal to the 78,000 newtons down. Okay, right, so that was the end of that part of the GCSE paper. We're not actually doing this question in the live stream, but I just thought I'd let you see my artwork. This was all drawn in PowerPoint, so this is something that you can draw just using simple programs. But this is for another question that we're not going to be doing, but this one, as you can see, is about like electromagnets. Okay, why is gravity not a force? Gravity is a type of force that causes, it's basically one of the kind of four fundamental forces of nature, and the attraction due to gravity provides the force on the object called weight. Okay, so that's kind of tends to be the way that we do it. Somebody's asking about JEE questions. Yeah, some of this is straightforward, and it's relatively straightforward, but you've got to remember there's a lot of stuff to cover, and I do cover harder stuff in some of the Olympiad videos that I've done. So basically, that was the end of GCSE. I think the time is pretty much exactly 8 o'clock. So for everybody doing GCSE, I'm going to have a break because nobody should be doing physics on a Friday night, apart from physics teachers, obviously. I won't be here Saturday, but Sunday I will be back in the evening at 7:30 as normal. And if you go to gcsephysicsonline.com/live, you can see all of my lessons ready for next week in terms of the subjects we're doing each day. And that means everything's already printed out, it's all ready to go. So I will see all of you on Sunday. Right. The next bit is for everybody out there who's just finished. We're just finished with GCSE and coming in for the A-level stuff. It'd be great to know in the chat if you're A-level or GCSE students. For A-level students, what are we doing? Okay, so random stuff in the chat. Okay, tonight we're doing a bit of, it's kind of like GCSE revision. It's A-level stuff. Hi Ben, hope you're doing good. Can I do AS paper walkthroughs? There will be some... Right. Okay, so I'm just seeing all the questions. Great to have everybody here. A-level Edexcel, A-level. Am I going to be doing a stream the night before A-level exams? Yes, I am. That's the plan. But to be honest, if you're only looking at that live stream, you've left it far too late. It's better to kind of start now, build up some good habits, and you still have plenty of time to kind of really improve your grade. You can actually find my schedule. It's not complete in terms of the lessons, but if you go to alevelphysicsonline.com/live, you can download the resources from tonight. So if you want to download a copy of this, and it's just a PDF that you can download and have a go at, you can obviously find this, you can find the stuff, or you will in the future be able to find the stuff for next week, and so on. Okay. AQA people are quite strong in the chat. Yeah, so basically I'm going to be doing live streams all the time, and I'm going to be doing live streams on the night before your exams as well. Okay, so let's have a look at this question. Now this one is an A-level practical that you do in year 13, but you will have probably done this maybe when you were in year 10 or year 11 as well. And for some of you, I suspect that this is when COVID happened, so you might not have done this practical for a long, long time, actually, when you did GCSE. Okay, so we've got an experiment to determine the specific heat capacity of aluminium. We've got this circuit set up with the heater placed inside an insulated cylindrical 1 kilogram aluminium block. Okay, so this is a circuit. We've got some electrical heating supply. We've got an ammeter to measure the current through it. We've got a potential difference measured by the voltmeter. And if you know I and V, we can work out the power being transferred. This is the symbol for a heater, which is basically just a resistor. I mean, a heater is just a big resistor where as you put electricity through it, it just heats up. We've got the reading on the ammeter stayed constant at about 3.4 amps. The voltmeter read 9.6. The following results were recorded for the temperature over 10 minutes. So far, at the moment, this is all pretty standard. Okay, so plot this data on the graph opposite. Now, when it says graph opposite, on the actual book, this question is from the not this book. Obviously, this book is great for year 13 at the moment. This book here is great for people definitely in year 12. I think to be honest, if you're watching this and you are in year 13, it might be a little bit late to be kind of getting the books for the questions, but this is ideal because this starts for year 12 students. This one goes up until the end of June, and then this one starts in July, goes over the summer holidays, and there's questions for the start of year 13. Okay, and inside it, on the 11th of July, which is the date we're looking at, you can basically see how this is kind of structured. And of course, I'm doing my salesmanship here. There's answers in the back of the book as well, so you can check, and also work solutions and videos on my website. So lots of good stuff there. So let's just plot this. While I'm doing that, the calculator, people are asking about this. This is just a lovely calculator, perfect for A-level physics. I know you might be using different ones in maths, but this is just the FX991EX Casio. I think it's just brilliant. It's got a nice, this one's even got a sticker on it. Look at that, you cannot buy that. So this is just like an ideal calculator, just so simple, nothing graphical, but it just works, you know. Right, so on this one here, we've been given the axes labelled, and I'm pretty sure that in any exam, you're not going to have to plot lots of data on an axis because it takes a lot of time to do that. So when it's 0, this is 20. When it's 60, it's 21. Then we go 22, 24, 25. Sorry, I'm just working my way through this. Okay, this is what we have. So the kind of data that you might expect, we can see we've only measured the temperature to the nearest 1 degree, but that's because that's the kind of standard thing you might have on like a calculator, on a thermometer in school. And obviously one of the dangers is that if you don't leave this on for long enough, or you don't have a high enough power, then the actual temperature change is going to be quite minimal. So we've got the data, and then we're going to use our ruler with a pencil. But the thing is, I would say, if you look at this data like this, you can see at the bottom, all of the points are going to be below the line of best fit. Okay, there's no way to get half the points above and below without them either being all under or all over. So in the chat, how would you draw a line of best fit on this? So what would you do to actually draw a line of best fit? Would you be doing a straight line that goes through the origin? Would you be doing a straight line that kind of does this? Would you be doing a curve, like a freehand curve? How would you approach a question like this if you had this data in an exam? What would be your approach? Let's just see what people say. Bang it through the middle, says Riza. Equal points on both sides of the ruler, says Ben. Straight line through the origin. A curve that merges to a straight line. Joe Smith, that is the best answer I've seen. Yeah, basically what we have, I think, here, is that we've basically got a straight line up here, but there's like a curve at the bottom. Okay, so I think that's it. So I'm going to do what Joe said. Okay, so we've basically got a straight line here. I'm going to turn the paper around, and then I'm just going to follow this down like that. So basically we've got something a bit like that. That's maybe not as good as it could be, but you get the idea. Okay, so basically that probably should go more like, you know, I'm just going to get a rubber. Okay. Which is of course why we use a pencil for our lines of best fit. No, that's rubbish as well. Okay. Is there a curve at the top? I reckon this is going to divide opinion, but I think the best way to do this is have a curve at the bottom and then a straight line. Now the reason for this is that basically when we're doing the experiment, I'm just going to draw it on the other side, what we have is, you often have this cylindrical thing. I'm sure lots of you have seen this at school. There's 2 holes in the top like that, okay? Now one of them has the electrical heater in it, and that kind of goes off to our electrical circuit. So that's our heater in this hole over here. But in the other hole next to it is where we have our thermometer, okay? And what that means is the second that you press go, the heater starts heating up. It's going to take a small amount of time for that heat energy to be transferred from here over to here. Okay, so there's going to be a small delay in the initial heating, and then after a while there's going to be this point where we have this kind of uniform heating, and that means we then later on in the experiment have this kind of uniform, provided everything's insulated, we have a uniform temperature rise because we've got a, you know, but at the beginning there's going to be a slight time delay between turning this on and actually recording the temperature. Okay, so as we're going through this lesson on simple specific heat capacity, we're looking at a kind of fairly standard procedure. Okay, now this is what we get. We basically have this kind of time lag at the beginning as that heat energy is passed from the heater through the metal block to the thermometer, and then afterwards we then have this region where we have a straight line. It says here that the heater transferred by the heater is, the energy transferred by the heater is E equals ITV. So the reason for that is that the energy transferred is equal to the power times the time. But of course the electrical power is equal to VI, and that means the energy transferred is equal to this electrical power, VI, multiplied by the time for which it's on. Okay. Okay, hopefully that's all good. Base your best line fit on the context of the question, Tommy. Yeah, this is because I want you to be thinking about stuff. So it's not a case of just plotting data and just kind of putting in a line of best fit without thinking what it represents. The reason I did this is because this is based on a real practical, and therefore it's not just theoretical. There are real things that you have to consider and like real life. So think about a bit of common sense about what this might look like if you were doing this in school. Okay, that's equal to the increase in thermal energy of the aluminium. So Q equals mc delta theta. I know it's a bit weird, but actually this is something I said, and this isn't just Bismarck Khan. It's not just for paper 3. This is like about specific heat capacity as well. I did something in this book here. So this is book 4, and I looked at all of the exam boards and the way that they represent this equation for specific heat capacity. So AQA at A level say Q equals mc delta theta, but where is it? Yeah, AQA at GCSE, the same exam board used delta E equals mc delta theta. Q equals mc delta T if you're doing A-level chemistry, doing AQA. So you can see that one exam board used 3 different equations for the same thing. Edexcel, delta E equals mc delta theta, E equals mc delta theta for OCR, Q equals mc delta theta for WJC, CCEA, EDUCAS, and then Isaac used E equals mc delta T. So there is no standard one formula. But the one that I chose to use for this was just Q equals mc delta theta. For all of you AQA gang out there. So equate the two things and rearrange to make delta theta over T the subject. So we can equate the two things and say that the energy transferred by the heater, which is ITV, and that's a nice way of saying it, is equal to the energy gained by that aluminium block, which is mc delta theta. Okay, and we want to make delta theta over T the subject. So the first thing I'm going to do is divide both sides by T to say that IV is equal to mc delta theta over T. Okay, so hopefully that's quite simple so far. And then we want to divide both sides by mc to get this on its own. So we can then say that delta theta over T is equal to IV divided by mc. Okay. Leela, would you be penalised for doing a straight line through the origin of the graph? I reckon if I was a teacher and I saw one of my students plot this and they did a straight line through the origin, I would just take their paper away from them and not give it back, and I'd make them do it again. That's in a lesson. I think in the exam they make it a really clear that it doesn't go through the origin, and they make it a really kind of big curve at the beginning. So yeah, right. So I would say that that's the best way of doing it. I think they probably wouldn't penalise you too much because it's only a slight curve at the bottom for that. So I don't think they'd penalise you too much. Great question. Janelle F. What does a gradient show? Right, so we've done that. Calculate the gradient of the straight line on the graph. So, I said this the other day, draw a big triangle. I'm going to do this to the line of best fit. So I'm going to go here to here. So, draw a big triangle, but only on the straight part of that. Okay, now of course, in the exam there's going to be a fair amount of leeway. In terms of like the answers that you could get. For this one here, I reckon that goes to about 35.5. So 35.5, take away 24, and that's divided by 600, take away 180. So in this case, that's going to be equal to, what's that, 11.5 divided by 420. Which is equal to 0.027. I was going to write it down here, 0.02738. Okay, hopefully that's all good. Everybody good in the chat so far? Everybody enjoying life, knowing that this is the pinnacle of your Thursday night watching, well, until the apprentice obviously, but this is the pinnacle of your Thursday night so far. So this is the gradient. So I would say that my value for the gradient would be equal to 0.027, and I'm going to give it to two significant figures. So why is it that we give that to two significant figures? Let me know in the chat. Why don't we give it as 0.02738 or 0.0274? So why is that two significant figures? Okay. It's given in the question. Yeah, so we do have in the question, I suppose, our data is two significant figures. Yeah, so I would say that this data for the temperature, this is given to two significant figures. That means our graph has only been plotted really to two significant figures, and that means we can only really give our final answer over here to two significant figures as well. Okay, so even though we have maybe 1.00 kilograms, we can only use the least, we can only justifiably give the least number of significant figures in that data. That time is only one significant figure. Yeah, okay, right. So, okay, we're just going to say that's two significant figures. Now, the other thing is that it's not the full answer. The gradient in physics, unlike maths where they just make up stuff, in physics it has a unit. And what we've got on the graph here, we've got degrees Celsius divided by time. So my unit for this would be degrees Celsius per second. Okay, and that's super important. This basically tells us every second how much hotter the aluminium block gets. Okay, right, so we've got this. Now, using your gradient and your answer to part B, calculate a value for the specific heat capacity of aluminium. Right, so the answer to part B is that delta theta over T is equal to IV over MC. Okay, so that's our answer to part B. But we also know that the gradient is going to be equal to the change in temperature with respect to time. So we can also say that the gradient is equal to delta theta over T. And that means if we can combine these two things together, we can say that the gradient is equal to IV over MC. And what we want to do is we want to find the value for the specific heat capacity of the little c. So we can bring this up here and divide by that to say that C is equal to IV divided by the mass times the gradient. Okay, I'm not using, you know, like when you use y equals mx plus c, we can sometimes use m to represent the gradient, but I thought that would get confusing having m times m. So the current is given as about 3.4, the potential difference is 9.6, the mass is 1.00, and the gradient, I'm going to use this value up here. So I'm going to say this is equal to 0.02738. Okay, so what I'm doing is not rounding down too early. So let's just work out what this is. So 3.4 times 9.6 divided by 0.02738 is about 1192. So I reckon, I'm running out of space here, that's about 1.2 times 10 to the 3 as an answer. Does that look right? And that's going to be joules per degree per kilogram. Okay, and this is the final answer. Okay, so basically the gradient, good question, Miles Easton Carver. The gradient represents the change in temperature per second. Okay, so what we're just saying is that if we know the time that it's heated up for, we can look at the increase in temperature. So the gradient in this case just happens to represent the change in temperature with respect to time. But for the previous part of the question, we also know from the energy supplied to the block is equal to the change in internal energy, or the increase in thermal energy of that aluminium block. And we can then rearrange this to say that delta theta over T is equal to IV over MC. Okay, So we know that this, the change in temperature with respect to time, is equal to IV over MC. And then that means we know that IV over MC is equal to the gradient. So we can use that to work out specific heat capacity. So do you have to use K for the units of temperature? It doesn't matter. You can use degrees Celsius or you can use K. But that's because 1 degree Celsius is equal to 1 Kelvin. They are exactly the same. They're basically, there used to be the centigrade scale, then they went to the Kelvin scale, and then the Kelvin scale is the basis for the degree Celsius scale. Okay. The real Joe Linton is 1255 in the range. Yeah, because with something like this, there's so much, there's so many kind of values that you could have had. I mean, if you'd drawn the gradient just that little bit longer, maybe, you might have said it goes down to here, and that would give you a different value. You might have said, well, okay, I'm just going to look at the values up here. And, you know, I think in any exam, there's often a fair amount of leniency about the numbers that you get. Okay, I think that's basically all I'd really had planned for the lesson today. Does anybody have any questions in the chat that I could go through for the last sort of 5 minutes or so? Okay, just going to get this bit out of the way. By the way, I've seen some good questions in the chat so far. Yeah, I'm basically doing, I'm going to be streaming normally about 4 or 5 times a week. And my plan is to do GCSE from 7 till 8 and then A-level from 8 onwards. What topics am I going to go through in the next stream? Right, I'll get my paper. Right, so next week, this is my plan so far. I haven't really properly done it, but we've got on Sunday, we're going to be looking at uncertainty, which is something I know lots of people found difficult. The Young's modulus is, there's 2 ways of doing it. There's one way which is like across a table where you can stretch out like a long wire. This is the other way using Searle's apparatus where you can hang stuff vertically. Again, it's like a kind of paper 3 AQA question style, but it's about a practical that you could be asked about in paper 1 or 2, depending which exam board you're doing. But we're going to be looking at uncertainty. On Monday, we're going to be looking at natural log and decay and some derivations. Then Tuesday, we're going to be looking at different ways of representing lines of best fit, and also looking at the trapdoor method for measuring G. So that's based on book 3. So we're going to be looking around. So look, again, this is what I've got in the book. So obviously, I know that some of you will already have done this. We're going to be looking at some lines of best fit and some worst and best, well, lines of best fit and worst acceptable lines of best fit. So we're going to be looking at that then. Then we're going to be looking at like this G by freefall. A couple of days later, we're going to be looking at using interrupt cards and also a ball on a slope. So this one over here, although it's year 12 stuff, it's still revision for anybody in year 13 as well, because all of you should know that stuff. Then on Wednesday, we're going to be doing some more stuff about decay, radioactive decay and natural logs and stuff like that. There will be something about the uncertainty in the line of best fit on Tuesday. Yeah. Right. So that's basically the thing. And I think it says down here in the chat that it says 8 o'clock for A-level each night. So that's the plan. But what I will be doing is I'll be putting that on alevelphysicsonline.com/live. Okay. Yeah, right. So more questions. Are there answers in the daily workout book? Of course there are. There are answers in the book. So you can just do a quick check of all the numerical stuff. But also, if you go to this page here, so basically there's a QR code. All you need to do is just scan the QR code, and then as if by magic, up comes on your phone. You will see all of the work solutions as well. So basically on your phone you can just download like the work solutions. So once you've done the question, you've had a look in the back of the book, you can then see for every day, obviously all the full, and this has taken quite a long time to be honest to do, you can see all of the work solutions for everything, including my approach to that. And of course, the other thing is that there's also videos. So if you want to see a video to that solution, and this is really aimed at Year 12 students. Now, Year 13 is too late. You just got to get on with the exam. But for those of you in Year 12, I've got questions for every day for like AS Physics and the first third of Year 13. Okay, any tips for moments? That's a good question. I'll do some more sloshy. I'll be doing some more moment questions as we go through the weeks. Is there any way to get the answers without having the book? Yeah, but it's only £9.99, Cara. Come on, it's only £9.99, of which I get about £2.96 because Amazon take the rest. So I'm sure if you were to search around my website, though, if you don't want to pay me any money, then you can probably search around alevelphysicsonline.com. Have a look in the section about books, and you can see a lot of the answers there. Okay, right. I think I'm just going to call it a day there. I hope all of you are well. I need to get back because I want to see The Apprentice. Who do you think is going to win? Is it going to be the pie guy, or is it going to be the person doing gyms? Because I know that Lord Sugar last year invested in somebody doing like kind of boxing gyms. So do you reckon it's going to be the gym or the pie? Let me know in the chat. Okay, right. Phil, okay. Rachel, will I be doing more videos for A-Level 3? I will be at some point, yeah, definitely. Pie, okay. Okay, Cara, yeah. Have a look on alevelphysicsonline.com. Go to the section on books, and you should be able to find links to books 1, 2, 3, and 4. Okay, not Phil. Right, Pie Man. Yeah, Sugar has carried him all the way, though. I think the thing is, a safe bet would be the pie guy because he's got the infrastructure, he's got the people, and he's got a big business, and he's got lots of cash in the bank. So I reckon Phil, the pie guy, might be the winner. And yeah, there we go. Anyway, it's great to see all of you tonight. And I will see all of you probably Sunday night, 8 o'clock, raring to go for the next week. And we're going to do some questions then looking at Young's modulus and uncertainty. Good night, everyone.